All right, so this is the second part of day 3, talking about parametric equations, and now we're going to start throwing some stuff through the air. So I think this is where it gets kind of interesting. Just quick little warm-up. Try these out. So given these 3 vectors, pause the video and try those 3. I'm going to write down the work for it, but just pause the video and try those 3 and see what you get. Okay, so there's the 3 finished products there. See if you got those right. So just multiplying, subtracting. Here we did some subtracting, and then the magnitude of that, and then here's a dot product. So now below here we got a distress flare. It's launched from a ship 75 feet above the water with an initial velocity of 76 feet per second. Now we're going to graph this against time. So we're going to let T be that driving force. We're going to look at the how is the X changing, how is the Y changing of this guy. Maybe you remember this, I don't know, from earlier in the year, but this is always your initial height, your initial Y value, and this number is always your initial velocity. As long as we're on Earth, we're going to use -16 if we're talking about feet per second. So that's gravity. You know, this number represents gravity pushing down. So this flare is actually shot straight up and it's coming straight back down. So the X coordinate will not change. But what we're gonna do, the X coordinate really should just stay 0 if I want to realistically see a side picture of this thing. But just to have it, to pull it out a little bit so we can kind of see the travel of it, we're going to say that X equals T, so that after 1 second you're 1 unit to the right, after 2 seconds you're 2 units to the right, just kind of drag it out. But really, this is just going straight up in the air and coming straight back down. So we really should just say X equals 0, or we say X equals 1 just to keep it consistent and watch it go up and come back down. But we're just going to do it this way just so you can see it. This is going to be the Y, so this is actually the height of it on our graph. So on your calculator, type this in. We're going to type it in here. It looks like this. And when we look at our window here, just to give you some hints, you could really just widen it out here, but how long is this thing probably in the air? I don't know. Let's just say, we could say for the sake of just guessing 10 seconds. I doubt it's going to be in the air more than 10 seconds. The X minimum, so X represents time. I really don't need to start any left of 0. I could go up to 5 or 6. I might just change to 6. And then for my Y is going to go up pretty high. Just kind of, so 0 is water level, so that's going to be the bottom of the graph. And how high does it go? I don't know, we'll just kind of guess. You know, you could say 250, maybe I'll put 250 in here. Put 250 feet there. Now if this graph, it goes off the screen, then I'm going to come back and change that. So I'm going to hit graph of this guy, and it looks like it's a pretty good graph. Remember, this is actually going straight up and then coming down. I just let X equals T to kind of spread it out across the screen so I can see what's going on, but this actually is going straight up and straight back down. So if I'm trying to solve for 1 second, then trace it and let T equal 1. So how high above the water is it at 1 second? Well, it's going to be 135. So it says, graph it and give the heights. So it's 135. At 2 seconds, I'm going to type in 2, hit enter. It looks like it's 163. At 4 seconds, I am at 123, and then at 5 seconds, I'm at 55 feet. These are all feet. So you can go back and write feet on all of them. So that's kind of how, using the calculator to do that motion. Now, what if we throw it, we don't throw, actually we're going to hit this one. Instead of throwing a ball straight up in the air and straight back down, it's actually pretty difficult to throw a baseball straight up in the air. Or hit it straight up in the air. So we're actually going to be hitting a baseball, so that means it's going to have an X component and a Y component. So say Kevin hits a ball 3 feet above the ground. So it's going to start, and I know this is a person throwing it, but the strike zone is probably about 3 feet off the ground. So it's a strike, you swing, you hit the ball. So the initial height is 3 feet. So the initial height right there is going to be 3. Initial speed, so it leaves the bat at 150 feet per second. Okay, so that is going to be my initial velocity, v sub 0. Now the reason why I'm going to do cosine and sine, because I want to break that up. So it's leaving 150, here's the bat, it's coming off 150 is the magnitude, 150 feet per second, but it's at an angle of 18 with the horizon degrees. So I want to break that down. The sign is going to be the y component. So how far up is it actually going? It's not very much. It's not really going up very fast. It's going more out because it's only an 18-degree angle. So the x component's more. Well, this is the x component. Okay, so when I do 150 cosine 18, I'm finding out what's the x component of that vector, and then 150 sine 18 is going to be the y component, because y only worries about the y component of it. So the x component is simply the x component of the vector times time. So as time passes on, we're assuming that wind is not slowing the ball down. We know that's not true. You know, after a few seconds, the ball is not traveling 150 feet per second anymore, but for what we're doing, we're going to negate that. Just say it stays the same speed the whole way, so there is no air friction involved. Let's see, will the ball clear a 20-foot wall that is 400 feet away? So let's type this in the calculator. So I'm going to go back here. My x is going to be 150 is the initial velocity, cosine of 18. Now this all needs to be in parentheses. I should have put my parentheses in first. T. And then for my y, I'm going to have negative 16t squared. Let me delete. I'm going to clear all this. There we go. Negative 16 t squared plus, and then in parentheses, initial velocity 150, sine of 18, close parenthesis, times t, and then plus 3, because that was the initial height of the ball. So now when I go to my window, again, I'm looking at a side view of this ball flying. I'm assuming the ball is not in the air. I'm going to say about 3 seconds, probably less than that. You know, if you can always overshoot it and then pull it back later. You know, kind of change that number later if you need to. The x, how far is the ball traveling? So I don't need any negatives because it's leaving the bat. It's not going in the negative direction. If I want to know 400 feet away, maybe I'll do 450 for my x max. This guy, you know, let's do chunks of 50. That way there's not so many marks on there. And then my y min, well, the ground is 0, and probably the highest it would ever go, maybe I'll just put 80 down. Again, you can come back and change this later. If it goes off your screen, make it bigger, you know, whatever you want to do. Now, I did do trig, and I'm given angles, not radians, or degrees, not radians. So I need to go back to my mode and make sure that I am in degrees also. So make sure you're in degrees. Now let's graph that guy. So there's the ball going through the air. Okay. So what I want to know when it reaches 400 feet, so my x value is 400, I can trace here, and now t is time, so I can't just type something in, but watch your x. When that gets to 400, how high am I? So about right there, it's almost 400. It's 7 feet off the ground. We're told that it is a 20-foot high fence. So it's actually going to, boom, hit that fence. So the fence here, if that's 7, it must be about this tall. And actually would hit the fence and fall down, so no, it does not. Just a little trick here. If I want to draw a vertical line, I'm going to use that same t, but I'm going to let, say, x. I want x to be 400 no matter what. So instead of having it in terms of t, it's just 400. There's no t to plug into, so x stays 400. And then the y, I just want to draw it. It needs to be 20 feet tall, so the highest it ever gets would be 20, and that's when you got your highest value. Now it looks like about 3 seconds to get to the wall here. So I'm going to say t divided by 3. That way at 3 seconds, this would be a 1, because 3 divided by 3 would be 1, and 1 times 20, so it's going to go up 20. It's going to be the highest at 20. So I'm going to go back to this guy here. I'm going to do 420. Let's see, this is not something I expect you to do. You can do the whole problem without. I'm just kind of showing you how to draw a cool little wall in there. So I do this, it draws a 20-foot tall wall. You see it does not clear the wall. So for various reasons, this one's a no. So no, it does not clear the wall. Will it clear the wall? No. No on that one. Okay, flip this guy over. Jessica is going to throw a javelin. She's throwing it from a height of 5 feet, so that's your y sub 0. The initial velocity is 65 feet per second. That's your v sub 0. Initial velocity at an angle of 45. So that's the best angle. She must be like college level or an Olympic level javelin thrower because she knows that 45 is the best angle to throw something. Now write the parametric equations to represent the path of the javelin. So my x, again, we want to break it down. We want to just the x component of that vector. So that would be, we use cosine, so it'd be 65 as your magnitude cosine 45 times t, and then the y is negative 16t squared plus, and this is where your initial velocity would be 65. Let me do this. So 65 sine 45. So that's the y component of the initial velocity. And then your initial height was 5. So your y sub 0 is 5. So after 5 seconds, how far has the javelin traveled? So you could put this in. It seems like a lot of work, but if I type it all in the calculator, then I don't have to do anything myself. So I'm going to type this in. So I'm going to change this to 65 cosine 45. And down here, I just need to change this initial velocity to 65. Change the angle to 45. Change the initial height to 5. And graph it. So it's not going as far, the baseball field. She didn't throw it out of the park or anything. But if I want to know after 5 seconds, well, t represents time, so I'm going to just go trace and type 0.5, and there's my x and y coordinates. So how far has the javelin traveled horizontally and vertically? Well, horizontally, so in the x direction, it traveled 22.98, so that's horizontally. And on the y direction, my y value is 23.98, but remember it started at 5 feet, so it really hasn't traveled 23, almost 24 feet. If I subtract 5 from that, it actually has traveled 18.98 feet vertically from release. So it is this far off the ground, but it's traveled that far up. Okay, so that's how you answer that one. Okay, so that I can use the graph to answer my questions quickly. Jane is riding a Ferris wheel with a radius of 30 feet. And this kind of probably looks familiar from Unit 4B. We're going to look at it a little bit different, though. We're going to look at it from parametric standpoint. The wheel is turning counterclockwise this way at a rate of 1 revolution every 30 seconds. Assume the lowest point is 6 feet off the ground. It's 10 feet off the ground, so 6 o'clock is 10 feet off the ground. And Jane is right here when it starts at time equals 0. So we want to do some parametric equations here. Now if it makes a circle, that means we're going to use x equals cosine, y equals sine. The radius then is you put a number out front. So for x, we say x equals 30, because that's a radius, cosine theta. Y equals, that's going to be 30 sine theta, but that is from a standpoint, this is already 40 above. It's already 40 above, so it's going to be 40 plus whatever this is from the wheel. So if you're at 0, you're actually at, so 40 plus 0, right here at A, you're still 40 off the ground. So you got that vertical shift up 40. Now, theta, though, we got to kind of take care of some of the time issue here. So how fast is it spinning? Because if I plug in 1, 2, 3, well, what does 1 represent? When t equals 1, well, that's 1 degree. Or if we're doing radians, I don't want t equals 1 to equal 1 radian, because it doesn't travel 1 radian per second. It actually travels 2 pi radians every 30 seconds. That's your speed, which if you reduce that, that'd be pi over 15 radians per second. So I need to put that in. So every time there's a 1 after 1 second, well, I want that to be multiplied by pi over 15. So for pi here, I'm going to do x equals 30 cosine, and then inside here I'm going to do pi over 15 times time. And then y equals 40 plus 30, and then in parentheses for theta, I'm going to have pi over 15 times time. So that way after, if it's 30 seconds, if I plug a 30 in here and multiply this out, it'll be 1 full revolution. So there's my parametric equations that models. There's my first answer. Now, after 22, I'm going to plug in 22 into these, and you can type these in the calculator and just do 22. If you want to, you could do 30 cosine of pi over 15 times 22, so it'd be 22 pi over 15. 40 plus 30 And this would be pi over 15 times 22. And you can type these in the calculator and the y equals and x equals, then do t equals 22, or you can just type them in like this. It's totally up to you. Up here I did it in the calculator. Here I'm just going to, or up here I graphed it, and down here I'm just going to type in the calculator. So negative 3.14, and that'd be, so you're 3.14 units to the left. And it just so happens that's pi, but you're like, oh, where are you going? Let's find out what the y is here. So the y is going to be 10.16. So you're going to be left 3.14, up 10.16 from the center here. So that's her location. That guy. So yeah, there's some more applications for parametric.